Alrighty, welcome back to 105. We have all survived the midterm. We lost a few people, but that's okay. You probably have other midterms this week, I assume. But that is quite unfortunate because we are back to regularly scheduled lectures where we start talking about the parts of C that make C, C. C? Anyways, everything we learned so far pretty much applicable to any single programming language. Java, Python, whatever. Today is the first thing we get a flavor of the fact that C does nothing for you and that you have to program everything yourself. So we've argued about memory a little bit. I've touched on, what a stack is a little bit, and we said variables for functions live in memory. We said it kind of acts like a stack. That will become more important today. So recall, local variables only exist when that function runs. So if I have this program that has a main that also defines a function called foo, which returns a pointer. If my function foo declares a variable called x, this x only exists as long as foo is active. So I assign the value 1 to it, and then I return the address of x. So that is a pointer, just a memory address that points to foo's x. And then when we return from foo, that x no longer exists. So this program has a bit of an issue. The pointer that's returned here will be pointing to some location which may not exist. We've seen this before, where that value of dereferencing p changes from time to time. It could be 1, could be a very large negative value, could be 0. Who knows? It's technically undefined behavior. So when we executed this, what happened is we draw all of our variables like before in main, starting with main. That's our first function that runs whenever we're running C. But now I will actually give this region of memory a name. So we called it a stack before because we're going to introduce a new region of memory today to kind of help us solve this problem where maybe we want to create or return a pointer to memory that didn't exist before. So in this case, what happens when we execute main, it'll create some space for a variable called p. Currently, it doesn't have that value. It will be an address. It will be a pointer. We don't know. We're going to assign the value to it from the return value we get from foo. So execution starts or then goes to foo. So main calls foo. Foo declares a variable called x, assigns the value 1 to it, and then we return the address of x. So we return a pointer, or we return an address that points to that value of x. And then after we return, that value of x no longer exists. So what we have is we have a pointer to some undefined space, which is why technically this is called undefined behavior. And when we ran this program, it did all sorts of weird things. So everyone remember that? Anyone have questions about that? This is a bad idea. All right, so we're good with that. So, well, can we return a pointer to memory created in a function? Well, from what we know now, we can't, because any variables in a function are, if we want to speak like true programmers, we'd say that they're allocated, which is just another way to say created in memory on the stack. So that previous region of memory. So that int x only exists in memory as long as we're running foo. So as soon as we return from foo, that x disappears. If we call foo again, it would create a new x. So in C, which is one of the things that makes C C, is we can explicitly allocate memory. So there's another region of memory C can use that is unrelated to the current running function. So the region of memory is just called a heap. And it is like the actual literal English word of heap, which is just like a pile of garbage. Well, not a pile of garbage, it's a pile of something. I say it's a pile of memory, it's a pile of something. So it's just a large amount or number of, in this case, memory. If you go on, this term gets used a lot in computer science. So there's data structures called a heap, but when you're talking specifically about heap in terms of memory, it's just some space of memory that we can use for our programs. So we can actually request memory in C using a function called malloc, and it's short for memory allocation. C programmers need to make everything shorter and I guess therefore cooler, so they just call it malloc. So it's short for memory allocation is how to remember that one. And its function prototype in the C standard library is this. So the function is called malloc. It takes a single argument, a size underscore t called size. Don't worry about that. Size underscore t is basically just a positive integer. So it has to be an integer. It's the number of bytes that you are requesting. So they just call it size underscore t just so it can vary depending on what CPU you're running on. For our case, we don't really care. It's just going to be an int. Just think of it as an int. It just has to be positive. And what it returns is a void star. So that is, again, C's way of saying it returns a pointer to what? I have no idea. I don't really care. So if we do size underscore t, like how many bytes does that type actually occupy? It's going to depend on your machine, but likely in your case it's going to be 8. You don't have to commit this to memory or care about it. We're not going to use a ton of memory in this course. So that size argument is how many contiguous bytes to allocate, and what malloc does is return a pointer to the starting address of that. And then you may use size contiguous bytes all in a row for whatever purpose you want. So for a single variable, for an array, you might notice this is pretty much similar to how an array is structured in memory. So you can use that memory for whatever you wish. That's why it returns a void star, because C can't know what you're going to use this memory for. It's up to you to cast it to the proper type, signifying whatever you want to actually use this memory for. And a lot in software, you'll see the term called API, stands for Application Programming Interface. Basically, it tells you how to use a library, like what functions it has, what types it has, all those sorts of things. So you might say something to your friend or someone else, or if you want to confuse Python people, like what's the malloc API? And they could say, oh, well, it takes a size and returns a pointer. And they'll be like, what the hell is a pointer? And you'll be like, I took C, so I know. So how this works is, again, you're getting a pointer. If you want to create a pointer to an int using malloc, you just have to be sure to allocate enough bytes to actually hold an int, preferably exactly enough to hold an int. So for example, how you would write something like that is I would malloc size of, so size of becomes important now because we don't actually want to remember how big our types are, right? So we can just use size of. So malloc size of int says I'm requesting memory that can hold enough bytes to hold an int all in a row, and it returns you a pointer. So in this case, I know the type I'm pointing to is supposed to be an integer, so C will let you do an implicit typecast from a void pointer to any pointer you want, so we don't have to do that explicit typecast. C will just let this fly. So the pointer we return, we know it's going to point to an int, so we do int star p equals malloc size of int. So currently the value it's pointing to is undefined, so it could be anything, but we know that that memory is actually valid. So any questions about this before we actually use it? Okay, so if we wanted to initialize a value, we could just dereference it and then set it to whatever initial value we want. Has a bit more steps than just using a local variable, but the benefit is it exists in a different region of memory that is not tied to the function it is currently executing in. So, if we wanted to change our program, so if we wanted to do the same thing and we wanted foo to return a pointer to an int and have it actually work and guaranteed to work, well, I can't do int x, because if I return a pointer to, like, take the address of x and return a pointer, well then it's not going to exist by the time foo is done. If, however, I malloc size of int, so I malloc 4 bytes all in a row, and I know that that pointer return should be pointing to an int type, then I can dereference it, initialize it to 1, and then return p. So I can return that value I got back from malloc, and it's guaranteed to still be valid. So if I do this, and then in main, I get that pointer back as the return value, assign it to p, and then I dereference p, I should get that value 1, right? So if I go ahead and run this, boom, I get the value 1, and this is guaranteed to work every single time. If I set the value, initialize the value here to something like 42, should still work, right? If I dereference it in main, it's 42. So now it can actually use some memory that didn't exist in main before it actually called this function foo. So any questions about that before we break it down step by step? All right. So just to slow it down and show it more visually, this is what happens. So in that program, again, we're going to start executing main. It will go ahead, and now we have 2 regions of memory. The stack for all of the variables that the function will use that will grow up and then grow down, and then the heap, which will just contain some memory that we get from malloc. So in this case, whenever we start executing main, we declare a variable called p, which is a pointer to an int. Currently, its value is we don't know, because we're going to assign the return value of calling foo. So when we execute this code, first we will call foo. Then in foo has its own variable called p, which is a pointer to an int, and it will assign that to whatever malloc size of int returns. So what that will look like is part of that malloc call will go ahead and grab me, in this case, 4 bytes from the heap. It will have some undefined value, so that's why there's a question mark to it, and it will return an address pointing to that value on the heap. So p, again, is an address. It's just a pointer, and it's pointing to this heap, which this current value has enough space to hold an integer, but it is an undefined value. We don't know what the value actually is. So everyone okay? All right. So if we dereference p, dereferencing p just works like what we saw before. So it would follow the pointer 1 step and access this value here. So if we dereference p, we'll be modifying this question mark and then assigning the value 1 to it. So we're changing that question mark or undefined value to a 1. And then when we return p, again, c is copy by value. So main will get a copy of this address as the return value, and then it will assign that address, so that address won't change, but that address is still pointing to that location on the heap. So mains p will have that same address that points to the location on the heap that is still valid. So now if we dereference p, it will be 1 in this case, and everyone will be happy. So everyone okay with that? Still exists, still all good. All right. So drawback and few other things that happen with this is malloc can, well, everyone's computer probably ran out of memory at some point, so malloc can actually run out of memory and return an error. So if there's no more room on the heap, which basically means your computer is out of memory, malloc will return null. So you should check the return value of malloc. Otherwise, if your computer ran out of memory and malloc returned null and you try and dereference it or use it somewhere in your program, probably something very bad will happen. and your program will crash and burn. Although if you are out of memory, probably your program is not in the best state to begin with. So usually it's better to crash earlier than crash later and maybe get confused. So you also have another responsibility, is you now have to deallocate memory. So previously we didn't have to worry about this because when a function returns, all the variables disappear. So they're no longer value, your computer can reuse the memory, everything is all well and good. So we say at that point the memory is deallocated, meaning you're done using it, it can be used for something else. For memory allocated with malloc, you have to deallocate it yourself. If you don't deallocate it yourself, your computer is going to assume you're still going to use it, it won't reuse it, and eventually if you do this enough times and don't actually deallocate your memory, anyone use Chrome that use like 20 gigs or something like that, or like 4 gigs of memory? Well, that problem stems from this. They essentially would call malloc, you're done with that memory, they forget to free it. If you keep your web browser open long enough and your program has this issue, it will keep wasting and wasting and wasting memory until you eventually run out of memory, and then it will go ahead and crash, and then you have to restart Chrome, and then it will be okay for a while. And the more places you forget to deallocate memory, the worse and worse this is going to get. So to deallocate memory from malloc, you have to use a function called free. And the function prototype from the C standard library is free. The name free just takes a pointer, so a void star, and the agreement is that needs to be the address returned from malloc. So that will go ahead and deallocate whatever you got from malloc. And then afterwards, you cannot use that memory pointed to by pointer, just like we couldn't use it before when we returned the address of another function's variable whenever that function no longer existed. Same idea here, and void and free returns void. It doesn't return an error or anything like that. It's up to you to use this correctly. So if you accidentally give it the argument where the pointer is null, then your program doesn't blow up or anything. Nothing bad happens. Just free just does nothing. So you don't have to worry about that. That's just in case that happens. So you can do something like this where as soon as I'm done in main, so when I call foo, that malloc's memory goes ahead, initializes the value to 1, returns it, and I use it here. After I printed off the value, I no longer need that memory anymore. So if I'm being a good programmer and I know I don't need it anymore, I need to call free myself. So I need to free p, say I'm done using it, and in C you have to do this. And this is what makes C hard, because you kind of have to do your memory management by hand. Why people call this manual memory management, and why some people use other languages where you don't have to do this thing. Although generally they run into the same problem, but they just don't know it. So forgetting to deallocate your memory is called a memory leak. So your program is using more memory than it actually needs to function. Again, like with Chrome or any other web browser or any program in general that runs for a long time, it's a really big problem the longer the program runs. So you might actually run out of memory and slow down other programs, or in the worst case, you crash that program, lose some work, or something like that. So you can use a tool called Valgrind to help detect memory issues, which is really, really, really good. And you might find it very useful when you start working on the labs that start to get more complicated now. So if you run your program normally using the terminal, like using build valid pointer or whatever the name of your program is, and why I suggest using terminal is to use this, you just put the word Valgrind and then a space in front of it, and then it will show you a whole bunch of fun information. So let's just see. So here is the version of my program where I forgot to free p, right? I only malloced it and I never freed it. So if I go ahead and I run this using valgrind, so valgrind valid pointer, and I run this, I'll see it shows a whole bunch of information. So this just says that, hey, it's running something called memcheck, a memory error detector, some copyright notice, the command we wrote, and then a bunch of numbers here. So these numbers with an equal sign is just an identifier for your program, so you don't have to keep track of these at all. And then here is just the normal output of your program. So in this case, I'm printing the value 42. And then when your program exits, it gives you a heap summary. So that region of memory, it tells you what the state of it was whenever you exited your program. So this is saying when you exited your program, you still had 4 bytes in use from one allocation. So that's what 1 blocks means. And it's saying your total heap usage when your program ran was 2 allocations and 1 free. It's off by 1. It's because of printf, so don't worry about this. We only did 1 allocation and 0 frees. And then here in the leak summary, it tells us like what we actually did. So if it says definitely lost, that means we have definitely forgot to free something. And it says, oh, if you want more information, then you just lost 4 bytes. You can run it with something called -- leak check equals full. So to do that, you just do valgrind and then just write exactly what it told you. So you can do leak -check equals full and run it again. And then when you run it again, it now gives you more information here. So here it says 4 bytes are lost in 1 block, definitely lost. And it tells you, so the way you read this is it's starting with the most recent thing at top and the oldest thing at the bottom. So it's telling us that, okay, we were running, the allocation came from running main. Main was running line 11, and then, oh, okay, well, it called foo. So while main was running line 11, it was in foo, and on line 5, which is this line, this is the malloc that I forgot to free. So it gives you a bit more information, and then this line is where malloc is actually implemented. This one is not your fault. So that's saying basically you find in your code like what the last thing your code did from the top, and that's where you probably leaked memory. So I forgot to free this malloc here. So after running it, I can be like, oh, okay, well, sure, I forgot to free P. So I can go ahead, add that free call to P after I'm done using it, and then compile it, and then I could rerun valgrind again, and hopefully it's happy. So now when I run it, it says in use at exit, 0 bytes in 0 blocks, and you want to see 2 allocs, 2 frees. All blocks were free, no leaks are possible. This is what you want to see when you start programming in C and using malloc. So you should probably get in the habit of using this. Again, not required, but highly recommended that you should do this and make sure the message at the bottom was all heap blocks were freed, no leaks are possible. That means you are being a very good programmer. So any questions about that fun, handy dandy little tool? All right, so if we also want to make this example a little bit better, well, we should actually check for errors, right? So it's possible that malloc returns null because my machine has run out of memory. Probably unlikely, but if you want to program defensively, which again is another thing I highly recommend, is whenever you call malloc, you can go ahead and check if P equals null. If P equals null, that means something very bad has happened and I should just give up running my program. So one thing you can do in C is you can type exit, and then by convention you can do exit failure. And what that will do is stop your program from executing and just stop your program immediately and say that, oh, indicate to the operating system that I had some type of error, or I can't make any other progress because it doesn't make any sense. And it should be noted too that this exit with that status it's exactly the same as returning from main. I can just do it from wherever, because normally whenever we return from main, that also exits our, whenever we return from main, that exits our program, right? It stops our program from executing. So turns out returning from main and the value we return is exactly the same as just doing exit success. It's just a little bit shorter and kind of just does it by default. But this line and returning from main are exactly equivalent. They do the exact same thing. They stop your program from running. They indicate that it's done. If I want to end early, well, if I detect an error in main, I could just return from main. That will also exit my program. But if I detect an error here and I just return, that doesn't end my program, and I probably just want to end my program. So it's better if I just call exit explicitly. I don't have to worry about what function I'm in or anything like that, and I should indicate that I've exited with a failure. So this is my full program that kind of does all the right things. So any questions about that? So programming defensively. Alrighty, so again, that exit function immediately ends your program. Function prototype in the C standard library is a function called exit, takes a single integer called status, and the return type is void because this function never returns, right? Your program just immediately ends. So this behaves the exact same way as returning from main. Again, that status tells the operating system whether or not there is an issue with your program, which it can ignore if it wants. But in this course, if everything goes as expected, you should just use exit success, which is just 0, or exit failure, which, spoiler alert, is just the value 1. So, some problems you have if you are using dynamic memory is, well, now I have to be careful that you should not use the memory after we free it. So, if I have something like this, where I malloc space for an int, and then I use that pointer, cast it to an int pointer called p, so I know it's valid, so I know it has enough room to store it. So if I execute this, I'll get an address back. That variable p will live on main stack. It will be an address, and it will point to 4 bytes on the heap, or at least enough bytes on the heap to properly store an integer. Then if I go ahead and dereference it, I'm accessing this value and then changing it or assigning it to the value 14. And then if I call free on it, well, then it disappears and it's no longer valid. I erase it kind of just like before when I showed you foo's x. So now if I print f and then try and dereference it, this is now technically undefined behavior because it is just pointing into the void. It is not actually valid by the time it actually starts to print. So if I go to my code and I execute that, annoyingly likely, if I compile this and I run this, it's called use after free, I'll see that, oh, hey, indeed, it does not do quite what I expect. So I get a random value of 20,168 for some reason. If I run it again, I get another random value, another random value, another random value, another random value. Hey, instead of using rand, you can just do this and get a random value, huh? Screw rand, this is more fun. Although, it kind of depends on your machine. I'm assuming if some of you use Windows or a Mac and aren't using the code space or anything like that, you might actually get 0. Kind of depends. Depends on your system. That's why we call it undefined behavior. So this, you might notice, aside from getting a random value, that nothing really indicates that something really bad has happened. So again, this is why I highly recommend, if you use malloc at all, you should use the tool Valgrind. So if I use Valgrind on this, it will thankfully yell at you. So it will give you some indication that something has gone wrong. So if I scroll up and see what the first line it wrote after its copyright message, I can see invalid read of size 4. What that means is I was reading memory that is currently invalid, and turns out like it just analyzes memory, so it's not quite sure what the type is you're trying to analyze or anything like that. But we know from our code that we were trying to read an int, so that's 4 bytes, so it kind of makes sense, and it gives us a whole bunch of information. So it's saying we were trying to read it at line 8, which happened to be this dereference right here, if we were to actually argue about it and as a person. And then it also says this was the read that was invalid, and then it tells us where the allocation was from and what was freed by it. So it's saying it was freed here. So this is saying when the free call happened. So it's saying, hey, this was freed on line 7, and when you allocated it, it was allocated, again, this is not code we wrote, this is the first thing we wrote. So it's saying it was allocated on line 5. So that gives us a lot of information. So this is the invalid read. This is when we said, hey, we were done with this memory. And this is the initial memory we said we got and we said we were done with. So it gives us all 3 parts of it to help us debug it. So if you run this and Valgrind complains about invalid read or invalid write or anything like that, you should panic immediately and fix it so that it does not yell at you. So in this case, this is called a use after free because I'm trying to use that memory after freeing it. Valgrind will just complain about invalid reads. So if I wanted to fix this, well, I need to move my free until after I actually use that value. So again, now if I compile it now, run it with Valgrind, I can see that Valgrind is now happy with me. If I scroll up, I just see the copyright notice and my program's output, and it actually gives me the value I expect. So questions about that? Alrighty, so again, to break it down, again, we malloced size P, allocated it, we freed it, then we tried to use it here. This was our invalid read, and it is called a use after free. So the value we read from memory being undefined after free, it's again called a use after free. You might also hear the term that P is called a dangling pointer, so it's not pointing to any invalid memory anymore. What I would suggest to you, you do not have to listen to me, but I mean, I've probably been programming longer than you, so you should probably listen to me, but again, you're free to ignore me. Good practice is that just set the pointer to null after you have freed it. That makes it so that if you try to use it later, instead of getting some random memory value back, your program's just going to crash, and it's better to know that your program has an error in it by crashing than it just doing something random every time. It's going to be way, way, way harder to debug. So this makes it so that even if you do try and use that memory, after freeing it, your program will just crash instead of having a random value, and then it will be a lot easier to debug. So now if you do this, we'll see a segmentation fault immediately instead of an undefined value. So if I go back to that example where I moved my free here, if I did what you told me, it's like, okay, I just free P, I should just set it equal to null, just as a precaution. Now when I compile, and even if I just run this without Valgrind, now my program will just say crash immediately and say terminated by the signal sigviv address boundary error. Don't worry about that, you'll learn about that in 344. That just means I have basically screwed up my memory. I'm trying to dereference a null pointer, which is bad. And again, this doesn't screw up Valgrind or anything like that. I could still run Valgrind with it and see it will also help me that it still shows me that invalid read of size 4, no problem, and it also yells at me with a whole bunch of other information because I forced it to crash. And if I want to see more information, yeah, I can just rerun it with this -s. So, other bad thing we can do is, which is what makes C hard, is you cannot call free twice on the same pointer. So if I make this error, which again, Wouldn't happen if I just set p equals to null after I freed it, because the second free would be a free on null, which does nothing. It's safe to do. But if I do something like this, you will get a runtime error, meaning your program will crash when you try and execute it. So another error. Let's go back. So if instead I did something like this, where I accidentally freed it twice, you might think that, hey, this is an obvious error, I won't do this. Well, once you start adding functions and everything into the mix, you might accidentally do this. So please, please, please just use Valgrind to help debug it, because if you do this and you run it, actually I called it double free. So if you do this and you run it, so it's called double free. When you execute it, it will say double free detected and then give you this crap about some cache too. Don't worry about it. It's like how malloc was implemented. You can ignore that. Just say double free detected and it immediately crashes your program. And again, if I use Valgrind on it, Valgrind will give me a whole bunch of useful information where it will say, as the first thing, invalid free. So it says invalid free at line 8. So this is the second free I did to it. And it tells me again that your first free was here on line 7. And what that freed was from line 5, so from malloc. So this is basically telling me what led to that double free. But again, aside from, like, I could have something like this where, oh, okay, I didn't have that use after free, but in this case I would have a double free. But again, even if you have a double free, if you did what I said and just initialize p equal to null after that, we won't have any problems with our program. So if we run this again, we won't have any problems with this because we set p to null. And then if we free a null, that just does nothing. So we're kind of prevent this error from happening. So again, highly suggest after you free, set it equal to null. So again, Valgrind, very useful tool. It will help you debug those two previous issues. It will let you know if you're accessing invalid memory, likely because of a use after free bug or a dangling pointer. It'll also let you know if you have a double free, what two lines called free, and then you can hopefully debug your program using that information as well. So you can also define functions that work on arrays. So you can actually do something like this. So let's say we have some functions called print array and randomize array. So print array just prints all the values of the array. Randomize array would just go ahead and initialize every single value in the array between some number between 1 and 100. So if we have these functions, right, these are functions we have written before, right? That would randomize an array, print an array, nothing that special here, right? Nothing new. So the fun thing about this is using dynamic memory now, what we can do that we couldn't do before is we can dynamically create arrays too. So you can use malloc to create arrays for us. So before, like, if we wanted to take the length of the array as an input from a user, we were previously screwed, right? Because we had to know whenever we compiled our code how many elements should be in our array. So with this, we can actually have arrays of any size we want. So in this program, I can ask the user to enter the length of the array, make sure they enter a number greater than 0, and then what I can do is, because malloc just returns a big block of memory, which is exactly what an array expects, I can just return, like, request size of int. So that's the size of each individual element of an array if I'm using this array, times how many elements I want. And this is what I get from the user. So this will return to me a big block of memory. And again, remember, we have array to k anyways. So this is just straight up using a pointer. Or I could use a type to use that I could do this as well. Oops. I could do this as well and use array decay if I want, or wait, no, I can't. In this case, array decay is only for declared arrays. In this case, I have to use a pointer here because that's what malloc expects. So here I make sure that I have enough memory because, well, the user could type a like 2 million or something like that, where maybe it's more memory than my machine has. So I should definitely check if malloc returned null. If it did, since I'm in main, I can return exit failure, which will go ahead and exit my program. If you want to be cautious and don't want to remember whether you're in main or not, of course, in general, you could just do this. It means the exact same thing. But then after that, I can randomize my array because I know my array length and the pointer to the starting address of my array, which is just whatever I got back from malloc. And then I can print the array. And then after I'm done it, I can free it. And then, of course, after I free it, I can set that pointer equal to null. So if I run this, we finally have our first more fun program. So if I do dynamic array and say enter the length of the array, I don't know, I could say 4. And then, hey, I get 4 random numbers back, right? Seems to work all the time. I could say 10, get 10 random numbers back. I could say 100, get 100 random numbers back. Neat, huh? So now I can declare an array dynamically, and I don't have to know ahead of time how many elements it has to have. And if I go ahead and double check, if I run it with Valgrind, I can double check that I actually freed everything. So let's say I did test it with 100, and I can see, hey, all heap blocks are freed, no leaks are possible. Joy to the world. So any questions about this program? All right, and another good thing, so we checked for values, so we could try it with like enter the length of an array, I don't know. 2, 1, da, 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 da. So this is probably a lot of memory, right? So let's see what happens. Oh, it crashed instead of doing something random. So that exit 1, I only can see it here. So my program immediately exited instead of doing something strange. And that 1 it returns, which means exit failure, just shows up here. And this is how you know whether or not your program crashed or not. So that 1, by default, at least in the terminal I'm writing in, if your program runs successfully, you will not see any numbers here. That indicates 0. If your program crashes, you'll see a big red number 1 here. So I can ask for, too many elements, and then I don't have enough room on my computer, and it crashes. Other than that, I could run it with, I don't know, like 10,000 will probably work, and I can get 10,000 random integers. I can have large programs now that just allocate lots and lots and lots and lots and lots of memory, which is really, really fun. So, no questions, no anything? Fun? So, if you don't have questions, you'll have questions when you start writing programs that use malloc and free and trying to debug your program. So just remember my rules should immediately, if malloc, again, not required, but highly recommended, check if malloc returns null. If it does, immediately exit your program, and then, that means you've ran out of memory or something, or more likely than not, maybe if array length was undefined, which someone has done on the testing servers and other courses, tried to allocate 200 gigs of memory, which failed, and they didn't check if it was null, so their program just tried to use 200 gigs of memory, and it wasn't great. So, other than that, you should just go ahead, if you free something, just set that pointer to null, just to be certain that, hey, your program might just crash if you try and do a use after free or anything like that. So with that, good luck on Real C, and we will pick it up again tomorrow. So